Good morning, students. I am Nagamani, JL Chemistry, Naidupeta. Today we are going to learn about physical properties of D block elements. Physical properties of the D block elements. What are the main physical properties? The main physical properties are, we have already known that the D block elements are heavy metals and they are having the high density. We have already known the metallic properties, that is metallic luster, and next one is the malleability and ductility. These are all the common properties of the any type of metals. So heavy metals will also show same type of properties like metallic luster, malleability, and then ductility. And second one is the high density. So what are the main reasons for these properties? We will discuss. So what are the main reasons for these properties that the heavy metals like D block elements will they will show. So first of all the transition elements display similar metallic properties. All the transition elements display similar metallic properties. That means they are all having the same metallic properties. What are those metallic properties? Like high tensile strength and ductility and malleability, high tensile strength and high thermal and electrical conductivity. Thermal and then electrical conductivity. So these are the main properties shown by the heavy metals. And next one, they exhibit HCP. They exhibit in different crystal structures, like already we have known that the CCP closed pack structure, HCP, and then BCC. So these are the main crystal structures of the D block elements. And zinc and cadmium, for example, zinc and cadmium, these will show HCP. Mercury is a liquid metal, whereas manganese also shows a peculiar crystal structure. Manganese will also show a peculiar crystal structure. So they are very hard metals. These are the very hard metals, except zinc, cadmium, and then mercury. Zinc, cadmium, and then mercury. Zinc and cadmium are very smooth metals, whereas mercury, it is a liquid metal. The only liquid metal present in the periodic table, it is mercury. And next one is they have the high melting and boiling point and low volatility. High melting point and boiling point and low volatility. What is the means of volatility? Volatility means vaporization, nature of vaporization. Low volatility means they do not get easily vaporized. So that is the main properties of the physical properties of the heavy metals. Here we have a graph here, that is, we will show that graph. Why they have hard metals? Why these physical properties are shown by the D block elements? That means they have the unpaired d electrons in their outermost orbits. Due to the involvement of that greater number of n minus 1 d electrons, greater involvement of the greater number of, that means maximum number of n minus 1 d electrons will involve in these metals. So they will show different properties. not only n minus 1 d electrons and ns electrons are also involved in the um, um, involve a greater number of electrons involved in the different properties. So they will exhibit the metallic properties due to the intermetallic bonding, due to intermetallic bonding. So, due to this intermetallic bonding, due to the involvement of maximum number of electrons or the greater number of electrons of n minus 1d and ns orbitals in the intermetallic bonding, so they will exhibit high melting point and then high boiling point. Here we have a graph that is we will observe the titanium first 3D series metals, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and then zinc. So these are the first row of 3D elements. So this red color denotes the first row of the 3D elements. Here the as per the electronic configuration increases, that means the number of d electrons increases, melting point will also increases. So chromium has the d5 configuration, so it has the highest melting point in this series, whereas from the manganese it will downfall to the manganese, that means at all of sudden the melting point of manganese decreases when compared to the chromium due to the filling of ns2 electrons and d5 configuration. So gradually iron increases, cobalt decreases, nickel decreases and copper and then zinc also very much decreases. That is about the, that means as the number of unpaired electrons increases, number of unpaired electrons in the d orbital increases, the melting point will also increases. Same will be shown in the 4D series and then the 5D series. In 4D series the metal is the molybdenum. It has the highest melting point and boiling point, whereas in 5D series it is tungsten or wolfram. It is having the highest melting or the boiling point due to the involvement of n-1 d electrons and ns d electrons, maximum number of n-1 d electrons and the n electrons. So that is the reason for the highest melting point and the boiling point of these metals. And next one is the the general properties of the d block elements. Next one is the general properties. What are those general properties? These are all the, we have already known, these are all heavy metals. So all transition elements, display typical metallic properties like high tensile strength, ductility, malleability and high thermal and electrical conductivity and metallic luster. And next one has the hard and have high density. They are all having the closed packed structures. Due to the closed packed structures, they have high density. Due to closed packed structures, we have already known that zinc and cadmium has the HCP, and mercury it is a liquid metal. So the differentiating electron into the same d shell due to the here it is the nucleus, first orbit, second orbit and then third orbit. As the differentiating electron, when we go to the observation of the 3D series, so it is the 3D1 to 3D10, that means 3D1 to 10, that is the electronic configuration of the 3D series. So the differentiating electron enters into the same subshell, that is the same 3D cell or same 3 shell, third shell. So the effective nuclear charge increases as the atomic number increases. effective nuclear charge increases as atomic number increases. So atomic radii decreases. Atomic radii decreases due to the increasing of the effective nuclear charge over the nucleus. And next one is due to the involvement of greater number of electrons from n-1d and ns orbitals in the interatomic metallic bonding. So the melting points rise to d5 configuration. We have already known the melting point rise to d5 configuration, and next gradually decreases from the ns to d5 configuration. ns to d5 configuration. Due to the stronger bonding, unpaired electrons are having the higher number of unpaired electrons. Due to the stronger metallic bonding, 4d and 5d series has 4d and 5d series. They have the higher enthalpy of atomization. Higher enthalpy of atomization. As the atomic number increases, atomization increases. Here we have this one is the 3d series. They have the low enthalpy of atomization. 4d series have the higher enthalpy of atomization when compared to the 3d series, whereas the 5d series they have the very high enthalpy of atomization when compared to the 4d series. That means 3d series have the low enthalpy of atomization and 4d series have higher enthalpy, and 5d series is also having the higher enthalpy of atomization. As the atomic number increases, enthalpy of atomization increases. That is about the trends in the enthalpy of the atomization. And next one is the variation in atomic and ionic radii. Variation in the atomic and the ionic radii. Ions of same charge in a given series show gradual decrease in radius with increase in the atomic number. That means as the atomic number increases, atomic radii decreases. Atomic number increases, atomic radii decreases with increase in the atomic number. So this is because the new electron, and we have already known that the new electron enters in a d orbital. Each time the nuclear charge increases by 1 unit. As the electron increases, the nuclear charge increases by the 1 unit. And the shielding effect of d electron. The shielding effect of d electron is not that much effective. It is not effective. The shielding effect of the d electron is not effective. So due to the poor shielding effect of d electrons, the atomic radius decreases from. Here we have the graph that the atomic radius decreases from the first element scandium to the zinc. So here we will observe there is a increase in the atomic radius of zinc due to the completely filled orbitals of zinc. That means it is the outermost electronic configuration of zinc is 3d10 4s2 due to the complete filling of these electrons. So there is a inter-electronic repulsions. Due to the presence of inter-electronic repulsions, the size of the zinc will increases from copper. size of the zinc increases from the copper. That is the reason of the atomic radius increase in the zinc. And next one is the atomic radius of the first series is less than that of the second series. First series means it is 3D series. This one is the 3D series, and this blue dotted line it indicates the 4D series, and this one is the 5D series. So we know that the atomic radius will be very less when compared to the 3D series, the 4D series and the 5D series. So because the 4D series and 5D series have the nearly same atomic radius. They have nearly the same atomic sizes. Why? They have nearly same atomic radius. So in 5D series, the 5D electron will enters after filling of 4f series, 4f orbital. Due to the poor shielding effect of 4f orbital, the atomic radius decreases. So they have the similar atomic radius in between these two 3D series and the 4D series. That is the reason for the similar atomic radius of the 3D and 4D series. For example, if you take zirconium in the 3D series, so it has the atomic radius of 160 picometers, whereas hafnium it has the atomic radius of 159 picometers. So here there is evidence that the atomic radius of these two elements when belongs to 4D and 5D series, it is nearly the same. That means one is 160 and another one is the 159 picometer. So it is the same, nearly same atomic radius. Why? Because before filling the 5D electron, it will completely fills after it will comes after the 4f orbitals. So the complete filling of 4f orbitals, they have the poor shielding effect. Due to that poor shielding effect, the effective nuclear charge increases as the atomic number increases and the atomic radius gradually decreases. That is the main reason of the similar atomic radiuses of 4D and the 5D series. So due to the similar atomic radius of 4D and 5D series, they will show similar chemical properties also. Similar chemical properties. They will show the similar chemical properties. And next one is the ionization enthalpies. Ionization enthalpies. Due to increase in nuclear charge, there is increase in the ionization enthalpy. So ionization enthalpy increases as the nuclear charge increases. So here the nuclear charge increases, atomic radius decreases. So these d block elements have the highest IP values. So the ionization enthalpy from left to right increases from the left to right. Ionization enthalpy increases from left to right. That means scandium to zinc and yttrium to cadmium and lanthanum to mercury. So the ionization enthalpy gradually decreases from the left to right. Why it is high? The removal of one electron alters the relative energies of 4s and 3d orbitals. If we remove one electron from either from the 4s orbital or from the 3d orbital, it will alter the energies of outermost orbits like 4s and then 3d orbitals. So the unipositive ion has a dn configuration. N means it may be 1 to 10. So the dn configurations with no 4s electron. For example, if you take scandium, it has the 4s to 3d1. So if we take this scandium 2 plus ion, it is 4s0 3d1. That means there is no electron is present in the 4s orbital. So due to the no 4s electron, only 3d electron is present in the scandium plus in their ions, unipositive ions or dipositive ions. They have the dn configuration with no electron in the 4s orbital. No electron in the 4s orbital. So the valency of chromium is lower. The value of chromium is lower because there is no change in the d5 configuration. Chromium has the ns4s1. If you go for the chromium, its outer electronic configuration is 4s1 3d5. So it is the, if we remove one electron from the 4s orbital of chromium, the d5 configuration does not change. Due to the unchange in the d5 configuration, the value of chromium will be, the ionization potential of chromium is low when compared to the other elements. So the value of zinc, it is very high due to the completely filling of the all orbitals, that is 3d10 4s2. So second IP of chromium and copper have very high. Second IP of chromium and then copper are the very high because the chromium has the half filled configuration, that is 3d5, whereas copper it has the completely filled configuration, that is d10. So due to that half filled and completely filled configurations of chromium and copper, they have the second IP value will be very high. IP2 is the very high. And next one, IP values give some guidance concerning to the relative stabilities of oxidation states. So it will denote the, it will guide the relative stabilities of oxidation states. The stabilities of oxidation states by the, we can conclude the ionization potentials. Stability of oxidation states. And next one is the, what are the oxidation states? It is very very important. Oxidation states. Element with greater oxidation state occur at the middle of the series. Here we will see the oxidation states of different elements of the 3D series, that is scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper and then zinc. This is the first row of the 3D elements, that is 3D series elements. So scandium is the first possible ion. It has the highest possible is the, its configuration is 4s2 3d1. So when we lose 3, when scandium loses its 3 electrons in the outermost orbit, it will show the +3 configuration. It will show the +3 configuration. When we go for the titanium, it has 3d2. 4s2 is the common for all the elements and its outermost configuration vanadium is 3d2. So when 4s electrons loses, it will show the +2 configuration. One d electron lose +3 and one another d electron, it will show the +4. So the maximum oxidation number of titanium is the +4. And next one is the vanadium. It has the d5 configuration, sorry 3d3 configuration. It has the d3 configuration. When d3 means 4s2 3d3, it has the 5 electrons in their outermost orbit, so its maximum oxidation number is +5, +2, +3, +4 and then +5. And next one, chromium is the, we have already known, that is 4s1 3d5 is the chromium electronic configuration. So it has 6 electrons in their outermost orbit, so it will show the maximum oxidation number of +6. So +2, +3, +4, +5 and then +6. +2, +3, +4, +5 and then +6. So these are the higher oxidation numbers of the chromium element. And the next element is the manganese. It will show +2, +3, +4, +5, +6 and then +7. So the maximum oxidation number of manganese is +7. Next iron, it will show the +6 is the maximum oxidation number due to 3d6 configuration, 4s2 3d6. 3d6 means it has one paired electron, only 4 unpaired electrons. So it will show the maximum oxidation number of iron is +6. And next one, cobalt. It has the 3d7 configuration. So +2, +3, +4 and then +5. The maximum oxidation number is +5. Nickel +2, +3, +4. Maximum oxidation number is +4. Copper +1, +2 and +3. And zinc, it will give only one possible ion, that is only the +2. Whereas the scandium, it is also having the only one possible, that is +3. So the first element and the last element, they will show only one possible ions due to the completely filled orbitals of zinc and only one electron which is present in the outermost d orbital of the scandium atom. So next one, what are the stable oxidation states of these elements? +2 is the more stable oxidation states of the all 3D series, and +1 for copper, it is also stable, whereas chromium, it has +3 and +6. Manganese has a +4, +2 and +4. Iron has +2 and +3. Cobalt is +2 and nickel is also +2 and +4, whereas copper +1, +2, zinc is a +2. So these are the stable oxidation states. These are the stable oxidation states of the 3D series elements. And next one is the maximum oxidation number is exhibited by the middle of the series. That is, in the middle of the series, manganese is the middle element. So it will exhibit the maximum number of oxidation state, that is the +7. So the electron with greater oxidation state occur at the middle of the series, that means manganese. And next one is the lower oxidation states are at extreme ends. That means extreme ends means here, that is scandium and then zinc. The variability of oxidation state is the characteristic property of the transition elements due to the incomplete filling of d orbitals. Due to incomplete filling of the d orbitals. That is the main reason for the variability of oxidation states in the d block elements. So what are the maximum oxidation numbers showing elements? So the maximum oxidation numbers exhibiting atoms are, in 3D series, it is manganese. That is, it is the +7. In 3D series, it is the manganese +7. And in the 4D series and 5D series, 4D and 5D series, it is ruthenium and then osmium. 4D series and 5D series is the ruthenium and osmium. Both will show +8 oxidation number. And molybdenum in 4D series, molybdenum, chromium and then tungsten, they will show the maximum oxidation number of +6. Molybdenum is in the 4D series, chromium is 3D series and tungsten, it is in the 5D series. And next one is the chromium +6. Chromium +6 in dichromate ion. And whereas manganese +7 in the permanganate ion. Manganese plus 6 in the permanganate ion. Low oxidation states are found when a complex compound has ligands. When complex compound has the ligands, it will show the low oxidation state. Low oxidation state. When the ligands are capable of pi acceptors, pi electron acceptors. When the ligands are capable of pi electron acceptors, they will show those atoms will show the low oxidation state. For example, FeCO5 and NiCO4, nickel tetracarbonyl and iron pentacarbonyl. In these two elements, this carbon monoxide, that is the carbonyl ligand, it will bind in the d pi p pi bonding. It will bind in the d pi p pi bonding. So due to the capability of accepting the pi electrons, in these two compounds, iron and nickel, they will show zero oxidation state. They will show the zero oxidation state. In addition to the sigma bond, they are capable of the pi electrons, and they will form the pi bonding with the metal atoms also. Due to the presence of the formation of pi bonding, in addition to sigma bonding in the metal atoms, they will show zero oxidation state. That is about the physical properties of the D block elements. If you have any doubts, you will ask your teacher and clarify your doubts.